Thank you. I'm a postdoc in CCSE Group Berkeley Lab. Acknowledgements to a lot of my mentors, Ishan Srivatsa, Andy Nonaka, Wei Chen Zhang, John Bell, and Anne Algrim. And also acknowledgements to Asker for funding this particular research. So the motivation for this, what I'll be talking about is more of a language interoperable interface or workflow. Let's say that we know that there are several mature AMRX-based PDE solvers. For example, I'll be talking about Inkflow, which solves for variable density and compressible Navier-Stokes equations. But there are applications based on these codes which need an additional feature that may not be available in the code, but it exists as a feature in a Python library. That is where you would like to use a workflow or interface like this. So the AMRX Python interface, it's implemented using PyBind 11. And what the interface offers is different in different cases. I'll be only talking about this multi-scale modeling of dense granular flows application, where what we needed is like an adaptively evolving data-driven model. And that feature exists in PyTorch. While there is a corresponding data-driven aspect for or model in C++ version of PyTorch, which is libtorch, there is more support for the distributed aspects in PyTorch compared to libtorch. And that is why we want to use this PyTorch or Python version. In another application, while I won't be talking about it here, I just wanted to briefly mention because the interface is different in different scenarios. In this second application, we are looking at multi-phase modeling in a bioreactor, which is what the corresponding simulation is. It's a multidisciplinary, multi-group effort. So we work, or our collaborators do metabolic reaction model development, and they always work in Python. And what we are interested in looking at is the metabolic reactions occur on individual cell scale. But we do the hydrodynamics on the bioreactor scale. In order to investigate the combined effect of both of these things together, it means that our C++ AMRX code needs to incorporate these metabolic reactions that happen in Python. So there is no data-driven model aspect in there. So that is how it is slightly different, the interface, compared to the first case. So simulating multi-scale systems, a lot of times if you take a very large scale system, what happens is that if you want to simulate this at the highest fidelity, it becomes computationally intractable. That is where you would have a low order representation. So when you have a low order representation, you end up with closure terms. And a lot of times these closure terms are not empirical models that can exist. And that is why you probably have to go and run a local high fidelity model to get this closure term. And I'll talk more about the same thing in respect to dense granular flows in the next slide. So coming to multi-scale modeling of dense granular flows, the objective or challenge is that can we accurately and efficiently model large-scale dense granular flows, where we are saying that we don't know rheology or essentially viscosity of the system, right? And that's the closure term. The way we do this multi-scale aspect is that for the large-scale system, which might have a billion or trillion particles, we consider it in a Eulerian representation or a continuum representation. Here in this particular case, the continuum representation is nothing but our Inkflow solver, which is the variable density incompressible Navier-Stokes equations. But for each individual cell, in order to get viscosity, that's not, we don't know the viscosity or rheology. To get that, based on local flow information like strain rate, you can run, instead of running a billion particle system, you run a 10,000 particle system to get viscosity for each and every individual cell. So if you take this direct hierarchical approach, where you say that I want to run a particle-based simulation, which is LAMPS, for each and every cell, each LAMP simulation on a single CPU will take about 30 to 40 minutes. So you can see how that if you do a direct hierarchical approach, it's not going to be feasible because you have to do that for every time step and for all the continuum cells that exist. And that is where we go for a more adaptive approach where we say that based on the existing information, which is the particle-based simulations, can we have a functional representation for this data? So you can think of, like, let's say I have pre-existing 5 data points that are from these particle-based simulations. I can identify regions where I might have to run new particle-based simulations, or in a way say that I can avoid duplicate entries, where probably I would have run those particle-based simulations earlier, so I don't have to rerun them. And you can see that anytime a new particle-based simulation is performed, you need to update your functional representation. And that is where this whole adaptive aspect comes, that your data-driven model needs to evolve as your continuum simulation progresses. And that's why we said that, as I said earlier, that this is available in PyTorch, and that's why we need Python for this. And we do this using multiple program, multiple data execution model of MPI. So what it does is that here we are using only 2 programs. It can do more than that. But what it does is that for each of the programs, it gives dedicated resources. So here I'm saying that program 1, which is our AMRX code or C++ code, is given A MPI ranks. And program 2, which is in Python, has the functional representation, to be more precise, an ML model, and LAMPs. So those are on the Python side. Then what is the role of PyAMRX in this? Our program 1 is in C++, but the program 2 is in Python, right? And we need data communication between these 2 different languages. The way we do it is using PyAMRX. We leverage PyAMRX because it was already available, right? And we didn't need a lot of effort to redo a lot of coding and things like that. And we wanted to leverage that capability. What more it offers is that because it gives you all the AMRX native data structures in Python, so you are essentially doing communication of AMRX native data structures across these 2 programs. One is in C++, one is in Python. And PyAMRX also offers other things, very simple, convenient helper functions, which can convert these data structures to NumPy when you have a CPU or you're running things on CPUs, or a CuPy array and PyTorch tensors when you want to do these on GPUs. And that's the reason why we are leveraging PyAMRX, so that we get this interlanguage interoperability. And here I'll basically talk about what happens in a single continuum step. So at a given stage, you can think like the continuum solver. To move forward in time, what it needs is viscosity, but that depends on the strain rate. So for the M continuum cells that exist in the domain, it sends this strain rate information to the Python side or Python program, where on a given state of the ML model, it identifies n new particle-based simulations that might be needed based on high uncertainty areas. So you perform these new n particle simulations where we say that n is significantly smaller than m. You update your ML model based on this new data. This is happening on the fly. You have an updated model. Now you can say that, well, I can now confidently provide viscosity for all the M continuum cells that exist in the computational domain. So which basically is what was needed to move forward in time for the continuum solver. And it can progress ahead. And this basically continues in a loop to move forward in time for the continuum simulation. And as a demonstration problem, I'm showing granular column collapse. You can think of a column of glass beads that are initially held at rest, and they are all of a sudden released. And because of the gravitational force, they'll start collapsing. Unlike water, which will continuously keep running, what happens is the granular column only runs out for a certain length and then stops, which is what I'm showing is the x velocity contour for a corresponding particle-based simulation, which was run using mfix-hexa. Thanks to Deepak and Will for including this capability. So yeah. And like I've been saying, we used a function approximation in there, but for this particular case, we used an ensemble of neural networks, but I'll say that our framework will also work with, we initially started off with Gaussian processes, and we leveraged ensemble of neural networks for this particular problem because we have certain properties that we know a priori about our viscosity model that are monotonic nature and convex nature, and incorporating these ideas into a neural network was straightforward, and that's why we chose this particular aspect. But you can replace this aspect with different things. And now coming to the computational efficiency that we achieved for this particular case, where we said that there's about 1 million continuum cells in the whole system, and we ran about 5,000 steps. So you can think the multiplication of those two things is the total number of particle-based simulations that would have occurred if you went for a direct hierarchical approach, but we only ended up using 14 particle-based simulations that were enough to get a very good representation of the viscosity which spread across 3 orders of magnitude. And here I'll be demonstrating like the corresponding how multi-scale approach looks with respect to a pure particle-based approach with also fluid in there, CFDDM, again using MFIX-Hexa. And for this particular case, it only had about 2.3 million particles. So we saw about a 3 times speed up. But we think that if you had even more particles, the continuum scale would be even more scalable compared to the corresponding particle-based simulation. And yeah, with that, this is basically the summary that I have. Thank you.
I still understand. So when you take your very first time step,
Yes.
What does it know? Must know something.
It has some pre-trained data, like let's say 4 points. We used 4 data points.
And then how does it know those are good enough for most of the cells?
So it doesn't, right? So it'll identify regions. Let's say you can say, let's say I have a range of where the initial 4 points are. And if you know there's a new point that's very far away, you definitely have to run a particle-based simulation for that point because your ML model is good at interpolation.
When you say far away, you're talking about sort of strain space?
Yes, exactly. So it's extreme points. You don't want to use an ML model in extrapolation regime confidently. So you'll say, I have to definitely run these particle-based simulations. And then once everything is inside that range, you then have to decide based on uncertainty whether you want to run a particle-based simulation or not.
So sometimes you start with 4, then you have 14 more.
Yes, eventually, by the time the whole simulation progresses, sometimes you would have only one new particle-based simulation in a time step. And we initially, for the problem setup that we considered, they were pretty much there in the first few initial steps. We got to 14 very quickly, and then later there was nothing. Like it was very quick. But yeah, sorry.
So you mentioned using neural network as a function approximation.
Yeah.
We also have that problem. I will present right after you.
Right.
Do you have, so do you determine how many runs and how many data you want to generate on the fly?
Yes.
Based on the training error?
Yes, based on, so because we use an ensemble of those, we can get some form of standard deviation or uncertainty. So we use that to verify if we want to run a new particle-based simulation or not.
Yeah, so you basically, you have the uncertainty or the error of your neural network.
Yes.
Oh, that's great.
This is probably out of scope of what you just presented, but have you compared performance of PyMRX to other solutions like portable data interface?
No, no. I think our intention was to probably avoid dependency on external things because these two were already available. Yes, there are limitations for sure, but.
And then one of your applications has to be Python, right?
Yes.
What if like there are applications that don't use Python but still?
This works. Like I mean, the MPMD framework works for 2 C++. That has already been there and has been leveraged in AMRX. Yeah.
I have a question. Still like understand the
Right.
So the application, the AMRX application has the data in its AMRX framework.
Right.
We have Python, so we have PyAMRX.
Right.
So you basically create like a
Multifab.
multi-fab domain.
Yes.
Recreate it on the
Yes.
PyAMRX side,
Yes.
and you do a data transfer to
True.
API.
True. Yes. And also, you don't have to create the box array information on the Python side. You can get that from the C++ side. That's a convenient function that is there. So you don't have to go back and like hard code those things.
So you build the structure and then you
Yeah.
copy the data.
Yeah.
Can I just
one more?
Yeah, I think that since there are a lot of PyMarx questions, there's like a separate PyMarx documentation you can check out. It's not like hidden within the MRX box. So
That's true. Thanks.
Speaker again.